Okay.
Fantastic.
It's accurate.
I just noticed that.
We were hanging out under the bridge.
I assume that's
That's how you die.
Yeah. Mine's 3. Or got 3 boosters.
Yikes. Slightly after.
You mean it wasn't me though?
Yes, I mean, one of your friends told me to do that, so he's the genius.
Yeah, my friend. Just drove my phone.
So I could never work this out myself because apparently when I googled it, it was saying that my phone is like older version, so it doesn't have QR codes. So I had to download the software to be able to do that. So that's why I didn't think of it. I thought, I don't know, I didn't think of it. So most websites that I was looking before, like Google Forms, I had to pay like $350 per month to be able to collect answers and all that. I'm like, I'm not gonna do that. But Google Forms were free. So I don't know, I thought anything charged just money. So this one doesn't. So. But as you guys see, if your phone like mine doesn't accept like QR code or you cannot read it, you still have the link. So you can use that too.
I'm kidding. For a while there, my links were super chat because we were outside. And I was like, I'm so happy to get back. Another day. And then put the passport. My crap. Dude, the other day, I was like, say what? I started choking on a face. Because I was just eating it too fast. I tried to inhale. And then I'm like, I'm choking on it. And these people walking away. Why? And I don't think for like, we die. Like, you guys what? I have 4. Don't look away from me. I'm gonna die. For why? For what? So, you see someone choking on a bagel. Just do that behind me. But we're not.
Okay, so if you couldn't go through the attendance, I'm going to come back to this slide, so don't worry about it. But make sure that you tell me your names after the class in case you don't do the attendance. So I'm going to spend like 3 or 4 minutes talking about mask policy. So I had after I saw the email of the president about not wearing masks or masks being optional, I had this speech prepared. And some of my colleagues told me that they just went to the classroom, everyone was still wearing the mask. So I thought maybe, that would be the case because some students just ignore emails. I thought maybe this is one of the emails that we didn't see. We come back, everyone has a mask. So now that saying, most people don't have a mask, so I'm gonna go with the speech that I prepared. So, as you saw in the email, also instructor has the power in a sense to tell their students to wear a mask. So I'm not going to have a mandate for you guys to wear a mask, but I'm going to tell what I'm telling you, that although masks are optional right now, they're going to see the numbers, and if they go up, they're gonna mandate it again. And since I have attendance mandatory in my class, I don't want anyone get COVID or flu or cold, right? So one of the good things about masks was that every year I was getting flu, and then from COVID, I didn't get flu or cold either, because literally we're wearing masks, right? So now, I highly encourage you all to wear a mask because, you never know, sometimes we're asymptomatic, right? And we may have something, but we don't know. And I have students that I interacted with them, I answered their questions, and 2 days later they said, okay, I'm sick. And I'm like, should I be worried? Did they have something? But since we were wearing masks, I'm more confident. So I highly encourage all of you to wear a mask. Although, as much as I love to see all of you guys' face, I like it that you're not wearing a mask. But to be safe, I highly encourage you to wear a mask, from next session. And if you highly, are against masks or you don't want to wear them, make sure if you have any symptom, don't come to the class. And as you notice, in some of your classes, including this class, some students cough, some students like blow their nose or like they sneeze. And I'm standing here, I still think that would they spread it to each other, or like to me? So I'm sure that if someone next to you starts coughing, you will be uncomfortable, right? I don't think anyone loves it. So for that matter, if you're not wearing a mask, make sure if you have any symptoms, and I don't care if you have like allergies, if you're like having a cold, flu, anything, don't come to the class. And I have your absence excuse. Just like email me that you're not feeling well, okay? Any questions about that? Are we good? I'll keep the attendance slide here. So make sure to have the filled out. The other thing is that when I was teaching chapter 1, I skipped the section about like orbital view of like bonding. So basically we talked about like atomic orbitals in Chem 101 and previously, at the beginning of this class, but we didn't talk about molecular orbitals. And now it keeps coming back to me, when I just like progress with the lecture, I realize there is no way around it. So I'm going to go back to chapter 1 and talk about, and I'm going to write it here, like 114, the orbital view of bonding. And as always, I'm going to post all the slides, so don't worry, if, you're falling behind when I'm writing. And the sigma bond. So today I cover sigma bond, and next session I'll go to the other type of bond. So I give you enough time to study and don't confuse them with each other. Does that make sense? And like always, I have like a video of Khan Academy because that's a legit website, and then I was recommended by my professors when I was studying like different courses. So most of the time they don't have errors in these videos. So I highly encourage you after the class to watch the video, and I ask you to read the book. Okay, so this is section 114, and make sure to read the book. And I cannot emphasize that enough. Just by coming to the class, doing the homework, you cannot succeed to the full potential in this class. You need to read the materials, okay? And anytime, even if I don't ask you, do you have any questions, just like feel free to raise your hand and ask me questions. Okay, so I prepared like these slides last night, and I'm also going to write as I teach, but I thought this would be faster if I have them prepared already. So if I want to write the orbital diagram of carbon, first of all, can anyone tell me what was an orbital? We talked about this before, like in chapter 1 briefly. What is an orbital? When I say orbital, what does that mean?
It's
Yes?
a place where the electrons are kind of orbiting the nucleus.
Yes. Yeah. So it's basically the probability map of where electrons can be around the nucleus. Remember? So previously, I'm not going to go through all the scientists who came up with different atomic theories, but in nutshell, they established that we have nucleus, electrons are around it. And Bohr said that electrons, are around the nucleus, and he had kind of like, he called them electrons being in orbits. But then quantum mechanical model showed that it's not quite orbits, these are orbitals, and it's like probability map. So you cannot find an electron exactly if this is the nucleus, or I guess I just write it here. If this is like the nucleus, you cannot say for sure electron is here. If this is like hydrogen atom, right? The electron, it has like one electron, right? It has one proton, no neutrons, and one electron, right? So we know that this This is the nucleus, and then this is the electron. But we cannot say for sure the electron is here, or here, or here, or here, or here. And all the possibilities, if we consider, we get something like this. Remember? And that was the s orbitals that were spherical, right? Remember these things? So what if we have like more than one electron? If we have like 2 electrons, or if we have like 4 electrons, right? So what happens then? You have like different orbitals, right? So if I want to write electron configuration, for instance, for carbon, do you remember how we would do that? So carbon, I want to write electron configuration. We would look at periodic table, see how many electrons carbon has, right? And then we see like in the periodic table, carbon, and then we see the number is 6. So 6 is atomic number of protons, right? But number of protons and neutrons are the same if the atom is neutral. So it has 6 electrons, right? So can anyone tell me the electron configuration of carbon? And I asked you in your first homework too, right? So technically you should know that. Say it. Anyone? And sometimes I had this conversation with some friend of yours that they say, I need like more class participation, and sometimes students are afraid to answer a question, or they think they might answer wrong. If you answer wrong, nothing happens. So just like feel free to participate. And as I told you, when I enter your final grades, the last day, when I see like 88, I look at the students and then think whether or not they participated in the class. If you have class participation, whether answering questions right or wrong, that doesn't matter. As long as you participated in the class, I changed that 88 to 90. So you get an A. So I encourage you to have class participation. Okay? And now you're not wearing masks either, so I can just remember the faces better. I'm going to encourage you to wear masks, but anyway. So can anyone tell me, with that being said, electron configuration of carbon? Yes?
Is it 1s2, 2s2, 2p2?
Okay. So what did you want to say?
I was going to say the same thing.
Okay, right. So do you remember that how electrons would fill the orbitals? They start from lowest energy ones, right? So 1s has the lowest energy, and then 2s, and then 2p, right? Any questions? Yes.
Is 1p something that exists, or does it go straight to 2p?
Straight to 2p, because whatever the number of n is, remember, so the principal quantum number, or like the number of orbits, if n equals 1, you have only one subshell or one type of orbital, one orbital type. And by type, what I mean is that, hopefully you can read what I wrote. So it's like if n equals 1, you only have s orbitals, one type, or like one subshell. If n equals 2, you have 2 orbital types, or like 2 subshells, which is like s and p. So that's why you don't have like p orbitals for like n equals 1. Great question. Any other questions? Okay. So now if I want to have like the orbital diagram for this, so one way to write it is just like this, but I like the way that your book wrote it better. So we distinguish between the energy levels as well. So here, if you consider this y-axis to be energy, you have like 1s right here, and you have like maximum 2 electrons in it with like opposing spins. Remember Pauli exclusion principle, you cannot have like more electrons. And then you'll be having 2s, right? So you have like, again, the same thing, 2 electrons here. And for p orbitals, we have like 3. So p subshell has like 3 orbitals. And then when we want to fill them out, we fill them singly first and then pair them up. Hans rule, remember? So we don't put like 2 electrons in the px. So we call them px, py, pz. So this is how we do for atomic orbitals, if you just have 1 carbon. But now we want to talk about molecular orbitals. So what happens when we have like 1 carbon and 1 hydrogen, or like 2 carbons, or in general, what happens to the orbitals when we have molecules rather than single atoms? Is that clear, the objective of what we're trying to do here? So here, if we have like, if we consider this dot as nucleus, or I guess I go a little more down, so I won't be having space issues. So if we have like nucleus here, and we have like the s orbitals, remember what was the shape of s orbitals? Sphere, yes, so they are spherical. So this would be, for instance, your 1s. And then 2s is similar, but it's just like bigger, right? And it already has the shape here, but I'm going to regenerate that so you'll have better idea. So since a sphere in the space, if you look at it from x direction, y direction, z direction, it's symmetrical, right? So that's why we don't put like x, y, z axis. Or we don't say px, py, pz, we just write s. But when we have p orbitals, depending on their direction in space, we can have like different orbitals. And do you remember what was the shape of p orbitals? Exactly, Dumbo-like, right? So if I want, I just use this color. Okay, so for that matter, depending on this, Dumbo, depending on which direction it has, you can have like along x direction, y direction, or z direction, and then I show you what I mean. For instance, if you consider this to be your y-axis, and then you consider this, and this is kind of like a straight line. So I apologize for the crooked demonstration. If this is like x-axis and if this is like z-axis, depending on, you have this dumbbell shape around x-axis, you have like, we call this px, we call the other one around like z-axis, and they are symmetrical, pz, and then we call this py. I kind of like distorted here. Py. Okay, and this is basically what I draw here with different colors to demonstrate. One of them is px, the other is py, the other is pz. Any questions so far? So this is just atomic orbital. And as you see, these are like hard to demonstrate on paper because it's just probability of an electron being like around nucleus. So this is like the best that we can demonstrate them. Any questions? Okay. So if no question, I go to the next slide. Now, again, our course is carbon compounds. It's like organic chemistry. We're really interested in compounds that they have carbons. As you saw, we studied alkanes, alkynes. We're going to study much more. So that's why we focus on carbon and then study carbon first. So here is just like the electron configuration, or like orbital diagram rather, for carbon. And as I said, the better way to demonstrate it is like this. So you have 1s, 2s, and then 2px, 2py, 2pz, and then this is how we fill them. Okay, and this is kind of like the picture that I just showed you in the previous slide. And now, what do you think happens? So considering the electron configuration for carbon, which is this, what do you think happens if this carbon wants to bond with other atom, let's say hydrogen. So what do you think happens? Any ideas? So sometimes when you just look at the photo, you may think that we have like one electron here, 2px, the other here, 2py. So carbon forms two bonds to fill these two orbitals, right? But that's not what happens. Or like, what happens in real life is that one of these electrons from s orbitals go to like 2pz, and now we have like 4 single electrons. And that's why the valence of carbon is 4 and it forms 4 bonds. Does that make sense? And I also wrote that here, that if you have like another hydrogen, that hydrogen brings this electron to higher energy state, right? And this electron goes from like s orbitals to p orbitals, right? And now we have like 4 lonely electrons that they are ready to form a bond. Yes?
Could you explain why the H would make the energy state higher?
So that's a great question. So why s orbital why a hydrogen atom makes the So basically what I'm speculating is that so if we have like the energy diagrams as I showed before, so energy, so we have like 1s, we have like 2s, and then so the difference between like 1s and 2s is like much more from like 2p, so basically these two energy levels are like closer to each other, but these two are like further away. So we have like 2py, 2pz, and here we have this. So, and then when we have like only hydrogen, we'll go here. So this is for carbon energy. And then when we have like for hydrogen, we only have 1. So I think, and I should like look this up to be like quite certain, but what I just can think off the top of my head is that when we have like this single electron, it wants to form bond with like and then we have like, for instance, if we consider like CH4, we have like 4 hydrogen atoms and we have like 1 carbon atom. So each of these hydrogens want to form bond with this carbon, and for the hydrogens to just like form bond, each of these, if it just like so first of all, we always care about electrons that are in the outermost shell. So for that matter here, we're dealing with like electrons that are in the n equals 2. And we're not dealing with like these 2 electrons here, we're dealing with these n equals 2 electrons, these 4 electrons. And then if we have like 4 of these, let me have like this is energy, and we have 1s and then 1s, and we have like 1s. So if we consider any other possibility, so one possibility, as I said, it might be convenient to just think that one of these electrons here forms a bond with this one, and then one of these one forms a bond with this one, and then so it's more feasible for the hydrogen atoms to kind of first break these two electrons in like one orbital, break them apart, and then one of these comes here, and then they pair up. So usually when we're talking about like chemistry and then we think about things, it comes down to the energy and entropy. So energy is basically, as I said, most of the times in nature, things want to have like the lowest energy possible, and entropy means that they want to have like more, we call that binazmi in Farsi. Basically, they want to have like more movements or like more number of atoms, but now we're not talking about entropy, so only energy. So if we consider all the possibilities of the things that can happen and we calculate the energy, this one would be the most feasible one. Does that make sense? Kind of?
Yep.
Great question. Any other questions? Yes.
So after all that happens, do you have to rewrite the formula to be 1s2 to s?
So after that happens, we just don't deal with atomic orbitals anymore. We're dealing with molecular orbitals. Yes. And how we write that, so instead of having like 1s, for like here, if you consider that, instead of having like 1s orbital and 2 p orbitals, rather, if you consider like the atomic orbitals, instead of that we'll be having 4 orbitals that are the same, like here. I kind of like crash one of them, and we call them sp3 orbitals, because it's like 1 share of s orbitals and like 3 of p orbitals. So we call them like sp3 orbitals. Does that make sense? Any questions? Okay. And basically this is kind of like demonstration of what I said before. But here I emphasize that instead of writing like 2s, 2px, 2py, 2pz, when we're dealing with molecular orbitals, we just say 2sp3, 2sp3. So 4 of them would be like 4 similar orbitals. Now they are molecular orbitals and they're ready to bond with 4 different atoms. Yes?
Are we ever gonna do anything with the 1s orbital? Or are we just gonna leave that kind of always with 2?
No, that doesn't participate in like bonding. It depends. If you have like hydrogen, for instance, that has like the only electron is in 1s, we deal with that. But we always look at we don't deal with the field shell orbitals, if that makes sense. Great question. Any other questions? Okay. sp3 orbitals that I just showed, right? So now, if we consider like, CH4, for instance, so we have like 1 carbon and then 4 hydrogen atoms. So this is basically the demonstration of what I wrote before in the previous slide for like only carbon, right? Remember, it has like, 2s, it has like 3 p orbitals when it's just like atomic, orbitals we're considering carbon, right? So now if I have like 4 hydrogen atoms, I have like 4 spheres in a sense, right? 1 or like, yeah, 4. So what happens is that each of these hydrogens form a bond with those 4. Does that make sense? So now we have like s orbitals for like hydrogen, and we have like p orbitals from carbon. So we have like hybridized sp3 orbitals. Are you following what I'm saying? So basically each of the hydrogens 1s orbital bonds with each of the carbons sp3 orbitals. And then we'll be having a tetrahedral structure. So we're not gonna get too crazy about molecular orbitals and then talk about like different combination and all that. Just for I teach you to the point that you can understand the terminology that we talk about like in chapter 3 or like in chapter 1. So as long as you understand the things that I'm saying in the class, you should be fine for your homeworks and quizzes and exams. Any questions? Okay. So these are like the pictures from your book. So instead of having the whole pages, I just like copied and pasted just the figures. So kind of like explain this, and then when you read them at home, they make more sense. So this is basically the summary of what we just talked about. That we have like, if you have like 2s orbitals, for instance, you see that in each direction that you look at them, like each direction, y direction, z direction are symmetrical. And then for p orbitals, however, depending on which direction we have, 2px, 2py, 2pz, we can have like different, orbitals. So that's why we denote them with like x, y, z. So we know which one we're talking about. And then if we have like, just hydrogen, we have like 1s atomic orbitals. But if we have like a molecular hydrogen, we have like ss molecular orbital. So that is just like more straightforward, like one sphere, the other sphere. And then depending on, so we use a terminology of sigma bond. And sigma bond is basically when you have like two orbitals coming together and they are like in the same direction. What I mean is that if you have like, you consider this one, you consider this axis, and then for s orbitals they are like aligned and their atomic orbitals kind of mix together, but they are like in the same axis. As I mentioned, for s orbitals it would always align, right? Because they are like symmetrical. So you cannot possibly have like an s orbital and like a p orbitals that they're not aligned in the same axis. Does that make sense? But for instance, for p orbitals, if they mix in the direction of the same axis, like here, you will be having sigma bond. But if they have like, they mix like the other direction, so for instance, one of them would be like from, if they mix like, from like this, not aligned, in the same axis. Do you know what I mean? Can I convey what I'm saying? We'll be having another type of bond that we're going to talk about them in the next class, most probably. Here.
So what's the difference between how the two s orbitals combine to make like the ss orbital? What's the difference between the ss and the p? Is it just like the energy level?
So energy, great question. So energy levels are different, yes, but it also depends on what elements are coming together to form a bond. So if we have like two hydrogen atoms, we have like 2s, basically one is from one atom, one is from the other atom. But if we have, for instance, two carbon atoms, right, we have like s orbitals that forming the bond. We also have p orbitals. So s orbital of one atom forms bond with p orbital of the other. So it depends on what atoms we're dealing with. Does that make sense? Great question, thank you. Any other questions? Good. And then here, just like summary of what I've wrote before, so I'm not gonna devote time to talk about this. And then again, you see that here, if you mix these two orbitals, along the same axis, we'll be having sigma bond. The same thing here, you see we have sp3, you have like sp3, and then the orbital clouds, in a sense, they just mix in this direction of the same axis. So we have like sigma bond. Yes? Yes, of course. Okay. And this is basically the fancier photo, I guess, much nicer photo than what I just had before. That you have like 4 sp3 orbitals, and then s orbitals of hydrogen forms bonds with these 4 sp3 orbitals, and then we get methane, CH4. Okay, and these are like different demonstrations. If you want to demonstrate a molecule, so you can have like different versions of this. Usually in the exam, whether I give you like this version or like this version, but these two are other types of demonstrations, so I thought to also include them so you'll be familiar with them. So here, we have like the traditional way of writing the molecules, and here remember that if we have like dashed wedges, they are like basically this one here. It extends. It's as if we're trying to demonstrate a 3D structure on paper, right? So this one is basically as if it's going, if you have like a piece of paper, right? It as if it goes down the paper, kind of like that's how we can just demonstrate that. And the other thing with the solid wedges, which is like if you had that 3D structure, it's kind of like goes out of the paper. So if you see like these, make sure to know what they mean. Does that make sense? Okay. And then ball and stick model, which is basically emphasizes on the bonds, so you can see exactly how the structures are. And then we have also a space filling model that it's emphasizes on the space that is occupied by atoms. So here, you have like a better idea of the size of the atoms and then how they bond together, I guess. But for like ball and stick, it just the focus is on the bonds. Okay, and you also have like the electrostatic potential map that it focuses on the electron distribution. And here, red indicates like partial negative charge, and then blue indicates like partial positive charge. So I thought to also include this, so you'll be aware if you like see like different figures in different books or like your own book, you know what these mean. Any questions? Okay. So here is also kind of like a summary and also adding some points to what we just talked about. So kind of like in line with what your friend just asked, the strength of bond depends on, the degree of orbitals overlap. So, if they overlap more, the bond is stronger. If they overlap less, the bond is less strong. And the relative energies of the atomic orbitals. So depending on if they have like higher energy, or lower energies, this bond strength would be also different. And sigma bonds can be formed by the overlap of 2 s orbitals. S and p orbitals end on, as I said, if they have like their ends, form bond together, right? And then 2p, so basically S and p is like this, SP is kind of like this figure. And then this is like 2 p's. And then if we have like sp3 kind of like the if you have like S and a hybrid or like 2 hybrids. So as long as they form bonds along the same axis, if you have like, write or draw the axis of the orbitals and they align, it would be sigma bonds. Does that make sense? Any questions? Okay. No questions about this. As I said, I'm going to space out what I'm talking about. So this session, we talked about sigma bond. I want you to go study chapter 1. And then I talk about other type of bonding next session. So I thought to just don't talk about both at one session, so you have the time to digest the information and don't confuse them with one another. So if no question about this, now I'm going to go back to the sweet discussion of naming compounds. So Can anyone tell me how to name the compound on the left? So what is the first step? Longest chain, yes. So, what's that?
With the double bond.
Exactly. So longest chain with multiple bond is right here. So in case you had also like triple bond, it would be the same. So what about this one? I have 1, 2, 3, 4. 1, 2, 3, 4. Can this be my longest chain? Why not? Exactly, it doesn't have a double bond. Let me just like erase this one. Okay, what about like this one? Can this be my longest chain? Great. So what is the second step? Now I found like my longest chain including the multiple bond. What is the second step? What's that?
Finding your substation.
Uh-huh. So
You have to number it.
So when we have like double bonds, triple bonds, or like single bonds, do I care about substituent first or which one is closer to the, so if I want to name this, should I go like this direction? So tell me 1, 2, 3, 4. Should I consider this or this? 1, 2, 3, 4. First one, right? So in this example, your double bond and your substituent or like branch are like either way you encounter that sooner, right? So both of them, if you consider like either of them, you get the same answer. But we usually first think about your multiple bond. So we start naming carbons. So we encounter multiple bond sooner. Does that make sense? Okay, so with that being said, which direction you guys said I should go? Blue one, right? Yes. So not this one. Maybe I can just like erase this one. Okay. So, okay. So how would I name this compound? Yeah. So first of all, I see that, my main root, how many carbons it has, right? And then I have double bond. What do I use when I have double bond? Exactly. Butane, right? And then what is the number of, so I should denote where I have the double bond, right? Would it be 1 butane, 2 butane, 3, or 4 butane? 1, right? And then again, you see, you have double bond here, and then you consider the lowest number that is attached to double bond. Does that make sense? So I say 1 butane. So what branch or substituent I have? Yes, 2 methyl, right? Any questions about this? So, and then here, just like 2 of the rules I wrote, so make sure to go, read the book, and also previous slide that I had all the rules. So let's practice this one real quick. So what is my longest chain? Is it like this one? So it can be, right? It can also be, this one, right? So whichever we can use. And if I want to name them, should I go 1, 2, 3, 4, or should I go 1, 2, 3, 4? Is it like the red one or the green one? So green, yes. So green. So how would I name the So why did you say green?
Closer to the start.
Closer to what?
To the start. Closer to the start.
So what do you mean closer to start?
You have more substituents to this side than this side.
Okay, but what do I when I have like double bonds or triple bonds? Yes.
The first substitution.
You want to encounter the double bond first.
Yes. So when we have double bonds or triple bonds, we want to encounter double bonds sooner. So if I write the red one, right? If I have like the red one, I would write 2-butene, right? Because here I encounter like the second carbon, I have like butane. But if I write the green one, what would I write? Okay. Yes, so this criteria is met, right? Because both of them would be 2. And now, after you know, so, again, this example is one of the examples that both directions you go, you encounter like the double bond the same distance. But I highly encourage you to write that to make sure that this criteria is met. After you have like, you took care of the position of the double bond or multiple bond, you see where you encounter the branch sooner, as your friend mentioned, right? So if I write the red based on like the red naming that I have here, what would be the name? Yes, 3-methyl. What about the green one? Exactly. So that's why we always consider the lowest number, right? So that's why this would be the name. And let me check if we write 2-butene and then 2. So 2-methyl, 1-butene. Any questions about this? Good? Okay. Now I have like, 2 more examples here. So just going through them quickly, you choose the longest chain that has like includes the multiple bonds, right? So I just go here that I have the answer. And then when you have like, so you have like a bromine, basically bromo group, and also methyl, right? And your name is butane, and then if you go like, this direction, you encounter the double bond, in the second carbon. So here would be the same distance, but you encounter like the bromo sooner. So this is one of the examples that, when the distances are the same, we go alphabetically, right? So it would be 2-bromo, 3-methyl. So 1, 2, 3, 4, and this is how we name this. Is that clear? Any questions? Good. And then here is another example. So you have like, 1, 2, 3, 4, 5, 6 carbons, right? And we name this way because you encountered the double bond sooner, basically the first carbon. And then the last carbon has like bromo, so it would be 6-bromo, 1-hexane. Okay? Like in a sense, when you have only one double bond. Okay. So now I want to introduce another terminology. So we talk, as you saw in the previous examples or kind of like in your book, sometimes you can have multiple double bonds, right? So not only one. So when you have like 2 double bonds, we have like the ending of like, diene. So this structure here would be, so we start naming from here, right? Because we encountered the double bond sooner. Any questions? Is that clear? So 1, 2, 3, 4, 5, 6. So you encounter like the double bond in the first carbon, right? 1, 2, 3, 4, and then the 4 carbon, right? And then remember, you always, when you have like a double bond, there are like 2 atoms involved. and then you choose the one that has the lowest number. So that's why this is like 1 and 4 hexadiene. Okay, so this is just kind of like what we agree, that if you have like 2 double bonds, we use like, you know, iene, diene. So this would be 1 and 4 hexadiene. And then if you have like 3 double bonds, the ending triene would be used, like here. So here again, you know, so if you go here, it would be 1, 2, 3. If you go here, it would be 1, 2, 3. So basically each direction you go basically is symmetrical, so it doesn't matter which direction you go. So it would be 1, 3, 5. I guess I just like clouded. So 1, 2, 3, 4, 5, 6. So it would be like 1, 3, 5 hexatriene. Yes.
So why isn't it like we previously used to do it? Why isn't it like di-X or like tri-X?
So if you have like, I guess this is kind of like how we agree to have like name these compounds.
Okay.
This is just like the IUPAC rules that they, you know, scientists agree, or like chemists rather, or like chemists.
Just like remembering how we like did it with the
Uh-huh.
alkanes.
Uh-huh.
We do like tri or di before the actual.
Uh-huh. So we use tri-di for like functional groups or like the branches. So I guess to not confuse them with the branches, instead of using tri-di and so on, we just use like another name to denote. So basically, when we have like double bonds or triple bonds or like 2 double bonds, we use like, we change the, you know, ending of the substance itself. Great question. And I have like more terminology, and we have like 1 more minute. So if you have triple bonds, and then if you have like 2 triple bonds, we use like diene. And then here I encourage you to go through this example, you know, because you're going to see that next week in your homework. So here it would be like 1 and 5 hexadiene. And again, you know, it's kind of like rhymes with wine, so eine. And then when you have 3 triple bonds, you have like triene. So here it would be 1, 3, 5 hexatriene. So again, you know, make sure to, you know, read your book, go through more examples, and